Hello and welcome to my second presentation on momentum, which I'm calling Further Momentum, which features approaches to use in more difficult A-level physics questions. And I'll end with a past exam question about a spacecraft. This may be best viewed on a laptop or tablet. See what you think. That's me, and that's Fez Physics. Check out some of my other YouTube videos, please. And here we have a reminder about some of the basics, the basic equations involving momentum. Force times time equals change in momentum, which equals impulse. And there we have it. But there is a little bit more. The law of conservation of momentum. Don't forget, you can gain marks by writing that down. But remember the proviso, provided we have an isolated system, i.e. no external forces are acting. Remember what we said about elastic collisions and about inelastic collisions. Now, when you catch a cricket ball, the idea is to draw your hands towards you, to pull your hands towards you as you're catching the ball. This effectively increases the time of collision, and so the force acting on your hands is smaller, and you feel less of a painful sting as the ball hits your hand, less of a force. If I drop a fresh egg onto a hard floor, the egg breaks. The force is large enough to break the shell. If I drop the egg from the same height onto grass, then we might say that the grass cushions the fall. But don't say cushions the fall in an exam. Examiners really don't like it. The grass increases the time of collision, and so the force acting is smaller and the egg doesn't break. Another alternative approach is to say that the grass absorbs the kinetic energy of the egg. That would be okay. But here we're involved and interested in force and the time of collision. Incidentally, some people hold competitions to throw a raw egg into the air and let it land on grass. If you're lucky, the egg doesn't break. If you're lucky. Remember that an egg is strongest when squeezed between the ends. Exactly. Now, if we think about the egg, force times time equals change in momentum. For the egg, the initial momentum, if we're dropping it from a certain height, the initial momentum is 0. But F times T equals mv. Now mv would be the same whether the egg falls onto concrete or onto grass. So if T increases, which it would do if you're dropping it onto grass, then F must decrease. And a similar idea you've probably already come across is behind the concept of crumple zones in cars. Now, here we have the first of two questions. A cricket ball is hit by a cricket bat. We've got the mass of the ball, we've got its speed, it's returning along the same path at 20 meters per second. The time of impact here is 0.05 seconds. We're asked, what is the change in momentum of the cricket ball? What is the average force exerted by the bat on the ball? Which of course would be the same as the ball on the bat. And I'm going to assume that the ball initially is moving from left to right initially, and that's the direction of positive momentum. So let's just look at the answer. F times T equals mv minus mu. So the change in momentum, 0.16 times minus 20, because it's coming back in the opposite direction, the direction of negative momentum, minus the 0.16 times plus 20, and that's minus 6.4 kilogram meters per second, or it could be Newton seconds. Now, for part B, force times time equals change in momentum. I've indicated again that the minus sign just gives the direction of the force, and that force works out to be 128 newtons, which is quite large. Now, just look, the time of impact here is 0.05 seconds. This second question is pretty much the same, except I've said the time of impact is 0.1 seconds. And what's the change in momentum of the cricket bat? Sorry, the cricket ball. The answer would be the same. What's the average force exerted? Well, hold on. The time of impact is going to be larger here, so we would expect a smaller force. Is that what we get? Same reasoning, force times time equals change in momentum. And indeed, the force is 64 newtons. So let me stress a longer or larger time of impact, and so we have less force compared with the previous situation. Now, helicopters. Would Leonardo's design here have worked? Probably not. And you can see down below the YouTube design, there are other designs for helicopter toys. But questions about helicopters are important. The key here, we've got the rotor blades of a helicopter. The key here is to think about what's happening in 1 second. I'm going to stress that 1 second again and again. The rotor blades push 2,000 kilograms of air vertically downwards each second. We're going to assume that the air is initially at rest above the rotor blades and gains a velocity of 10 meters per second. That is an assumption. So what is the increase in momentum by this mass of air in 1 second? What force does this produce on the rotor blades? And what is the weight of the helicopter plus load? Think about that for a moment. Part A, mass times velocity. Part B, force times time equals change in momentum. Part C, weight equals mg. And here we've got some answers. Change in momentum, 2 times 10 to the 4 kilogram meters per second. What force does this produce? 2 times 10 to the 4 newtons. Okay. The mass of the helicopter plus load is given, so we've got the weight as being about 1.8 times 10 to the 4 newtons, and we've not got too many significant figures. Now we're also asked what unbalanced force acts on the helicopter and what vertical acceleration does the helicopter now experience? Well, for part D, we've got to take into account the upward force and the downward force, yes, and subtract them. For part E, which equation? Yeah, that's right, F equals ma. And just look at the calculation here. We've got the upward force, we've got the downward force. We've already worked those out. And so we've got the unbalanced force acting, 2.3 kilonewtons, F equals ma, as we said, which gives an acceleration of 1.3 ms to the minus 2 upwards, of course. Now, let's look at this question. A hose pipe has a cross-sectional area as given. Water leaves the hose pipe at a horizontal velocity of 3 meters per second, hits a vertical wall, and runs down to the ground without rebounding off the wall. We've got the density of the water, what force is exerted on the wall. How to approach this? Well, again, let's consider what happens in 1 second. In 1 second, a 3-meter jet of water will be hitting the wall. What's the volume of that water? Yeah, it's the length times the area. Okay, we've got the volume. Can we work out the mass of that water? Yeah, density is mass over volume. So I've worked out what the mass of that water hitting the wall in 1 second actually is. So now, force times time equals change in momentum. The final momentum, mv, is 0. Of course, we're talking about what's happening horizontally. And you can see I've got some information in there. So let's put in the numbers. F times 1 equals 0 minus 0.9 times 3. And we get minus 2.7, which is the force of the wall on the water. The force of the water on the wall then would be 2.7 newtons. Now, let's look at this question. A lorry accelerates from rest. The graph shows how the momentum of the lorry varies over the first minute. How would we go about this question? Well, remember my previous advice. Look at the y-axis. We've got 10 to the 4. Circle that. Remember it. Don't let that slip in any subsequent calculation. Okay. So the questions were asked to define momentum, state the physical quantity represented by the gradient of the graph, determine the magnitude of this quantity at 20 seconds, and to explain the shape of this graph. Okay. Let's move on. There I've circled the 10 to the 4. To define momentum, momentum is mass times velocity. Yeah, I've been very teacherish and I've put in the units. State the physical quantity represented by the gradient. Well, force times time equals change in momentum, delta P. So F equals delta P over, well, delta T. So delta P over delta T, look at the axes, isn't that the gradient? So the gradient represents the force. And yes, that force, that gradient, is decreasing as time proceeds. We'll come back to that in a minute. We're asked to determine the magnitude of the gradient at 20 seconds. Yeah, carefully drawing a tangent to the curve at that point. Make sure you draw in a large triangle. Examiners don't like small triangles. And you can see my calculation. And I get about 1.4 times 10 to the 4 newtons. Examiners would give you a little bit of leeway either way, of course. Now, we're asked to explain the shape of this graph. And yes, we should certainly be talking about the gradient, which we've already explained. The gradient decreases as time increases. So the force acting decreases as the speed increases. The rate of change of momentum is decreasing. Why? We might suppose that air resistance would be increasing as the speed increases. And that would be enough for our second mark. But maybe we'd think a little bit further. Perhaps the force provided by the engine decreases at higher speeds. Perhaps because transmission friction is increasing at these higher speeds. But the first 2 points are enough. And that is a past exam question. Now, I hope you like my Tintin poster. Just look at that rocket. Would Elon Musk be happy with that? Well, maybe, maybe not. A spacecraft called Deep Space One, mass 486 kilograms, uses an ion drive engine. This type of engine is designed to be used in deep space. The following statement appeared in a website. Read it carefully. The ion propulsion system expels 0.13 kilograms each day. The ions are expelled at a speed of 30 kilometers per second. The speed of the spacecraft is predicted to initially increase by about 8 meters per second each day. Use a calculation to comment on the prediction made in this statement. Right, we've got 4 marks. 4 marks to work for. And let's think about how we should tackle this. Yeah, first of all, read the question twice. A diagram might help with our thinking. And isn't it potentially a bit confusing that we have days and seconds mentioned in the question? Now, you know that I prefer to think about what's happening in 1 second, and I would generally recommend that approach to you. So let's move on. And from my diagram, there's the spacecraft. It's pushing out to the left 0.13 kilograms worth of xenon per day. Each ion is picking up a speed of 30 times 10 to the 3 meters per second. I'm calling that U. The spacecraft, we think it has an increase in velocity, delta V, of 8 meters per second per day. I'm taking anything to the right as having a positive momentum. These are all ideas that we've worked with before. Now, let's think about what's happening in 1 second. In 1 second, the total momentum before expelling the xenon equals the total momentum after expelling the xenon. Before, 0. After, big M times V for the spacecraft minus mu for the xenon. Remember, the xenon will have a negative momentum. And quite clearly, mv equals mu. So what can we now say? Well, I'm considering what's happening in 1 second. So for the xenon, delta mu equals, now it's 0.13 kilograms per day. So I've divided by the number of seconds in a day. I've got u. So that's going to give me the increase in momentum in 1 second. I've done that calculation. You can check it if you like. For the spacecraft, delta big M times V equals 486 times V. Its mass isn't changing much, and we'll come back to that point in a minute. V is what we have to find out. So delta mu for xenon should be equal to delta M big M times V for the spacecraft. So 486 times V is 0.041, and that gives V as being 9.929 times 10 to the minus 5 meters per second for the spacecraft. So in 1 day, delta V should equal that times the number of seconds in a day. Yeah, that's logical. And that equals 8.02 meters per second, which is roughly 8 meters per second. Okay, now we've done well so far, but let's take this question a little bit further. Each day, this spacecraft will expel 0.13 kilograms of fuel, and that represents 0.03% of the original mass. It's not much per day. I suppose there are 150 kilograms of fuel included in the 486 kilogram mass of the spacecraft. It should last for quite a few days, or if we work it out, about 3.2 years. Okay. Let's go a little bit further. Now, we might suppose then that the increase in speed would be the number of days times the increase in speed per day, which is about 9,200 meters per second. Yeah, that seems reasonable, but it would be more than this. So we come back to the idea of the mass. over a period of time, the mass will decrease. F equals ma, we would suppose that the thrust from the ion engine would be constant. So the mass decreases, so the acceleration increases. So as the spacecraft decreases in mass, the acceleration increases. Ion drives do exist, and you could try to find out more about them. They have their advantages and disadvantages, which examiners often ask about, albeit for 1 mark, and we need all the marks we can get. So keep working, and I've got a visitor. I've got to run. Thank you very much. Keep working.